All right, okay, so hopefully you had a chance to actually sit down, talk, and think through this, because this is a really good indicative problem of what you could see possibly on the AP exam, especially on one of the newer pieces of exams. So let's kind of go through and look at this together. An experimental apparatus represented above, and just so you can have an idea what's going on here, we have a glass tube, and we have two cotton balls at the end of those, or at the end of the tube. Both of these contain two substances, HX and a volatile base, which really just means that they can turn into a gas easy. Okay, so we have gases spreading throughout this tube, and the cotton balls are placed at the end of the tube at the same time. The gases diffuse from each end and meet somewhere in this middle section, okay, where they react to form a white solid. So this is the key. We'll actually see where the reaction occurs, because a white solid will form as the two actually interact with each other. Which of the following combinations will produce a solid close to the center of the tube? So a little bit of physics is tied in here. We want the gases to meet somewhere in this range. Well, how is that going to happen? If I release them at the same time, for them to travel the same distance to meet somewhere in the middle, they have to be moving at roughly the same speed. Well, what controls how fast a gas moves if they're all at the same temperature? And I believe this should say somewhere on it that it's all at the same temperature, or we assume it's all at the same temperature because it's all in one apparatus. So if it's at the same temperature, what allows the gases to move around the same speed? Well, we think back to the fact that temperature is a measurement of kinetic energy. So both of these gases will have the same kinetic energy, and kinetic energy is equal to 1/2 mass times velocity squared. We want our velocity to be same or similar between these two substances. So if that's the case, and we know this is the same, what does that tell us about our mass? It also has to be the same, or again, similar. There is some variation here just because of the fact that not everything's going to have the same mass, but could have similar velocity because the masses are close together. So how do we figure that out? Well, we need to calculate our molar masses for these guys and compare them. Now remember, you don't have a calculator on this section, so we kind of are going to freehand this. So we have hydrogen, which is essentially 1, and chlorine, which is essentially 35. So we're going to say hydrochloric acid is 36, and the nice thing is they give you 2 of them. So we'll put 36 and 36 for our molar masses here. Bromine is about 80, and hydrogen's 1 again, so we're going to say 81 and 81. So those are kind of our molar masses for our first substance. Now check out these guys. We have carbon, which is 6. Carbon is just 12. I just looked at its atomic number, not its molar mass. My bad, guys. Try that again. Carbon, which is 12. We have nitrogen, which is 14. So 12 plus 14 is going to give us 26. Plus the 4 from here gives us around 30. Okay. Nitrogen, again, we have our 14, plus we have 3, so we'll call this guy 17. We have this guy down here, which we just calculated, which is around 30, and we have 17 again for our ammonia, our NH3. So now, again, what we're looking for is the same or similar mass so that our velocities are the same or similar. So we have 36, 30, 36, 17, 8130 or 8117, and our best answer for the closest atomic masses is going to be A, and again that's going to solve into our equation, keep our velocities about the same, and therefore they're going to travel the same distance over the same time frame. Because remember, velocity is nothing more than distance traveled over time. So if they're meeting at the same distance, they have to be traveling the same amount of time. Okay? Alright, now what else this leads into? So we know the AP exam is very data-driven, and one of their new pieces of data they like to show us, which is actually really important and really a good piece of data to look at, is called a Maxwell-Blotzman gas distribution curve. What in the heck does that mean? Basically, it's kind of like a bell curve, so don't let it stress you out. What it does, first and foremost, we need to understand that these curves are anchored at 0. This is a velocity of 0. Well, what does that mean if it has a velocity of 0? It means it's not moving, which essentially means 0 Kelvin. So yes, we have the potential for 0 Kelvin in all situations. So remember, what we're looking at is average temperature, therefore average velocity. Again, notice there's not a lot in this range if you're thinking your bell curve, but there's always that potential. So these will always be anchored at this 0 point. From here, we've got a little bit of calculus, but not too much. The distribution will be the highest at the average point. So like if I go down closer to the center, but close enough, whatever this velocity is would also correlate with my average kinetic energy in that center portion. So notice this is about 100 degrees Kelvin. So whatever this velocity is, it would correlate calculation-wise to about 100 degrees Kelvin. Notice this one. It's got a little bit lower hump, okay? But notice where its center point of that hump is. It's a little bit higher on the velocity. Well, why is it going to be moving faster? It's going to be moving faster because it is at a higher temperature. And also keep in mind, this is the same gas sample for all 3 of these data points. And I should have mentioned that earlier, apologize. Okay, notice the next one. We have our center point again is the top of this hump. And we're going to go all the way down. Notice it's got a higher velocity as well. And that's because it's now at 400 Kelvin. Notice what's happening with these curves. Over here is a probability. Also, what you may see over here on occasion is a number of molecules or moles. Could be another thing you could see over here. But probability and the number of molecules kind of go hand in hand because the more molecules you have, the higher the probability. Okay, but what this is where the calculus comes in, and we're looking at the area under the curve. If you were to calculate the area under all 3 of these curves, what you would notice is they would all equal each other. Area equals the same for all 3 of them. Well, why? Because it's the same sample of gas. Therefore, the number of molecules has not magically changed because I have increased temperature. And again, we would also assume that this is a rigid sealed container, so the gas is not able to escape either. So notice what we have a higher hump here, and that's because it's a shorter distance between here and here. And again, why is that the case? Because I have to show a lower velocity. So I'm kind of scrunching up the curve and bringing it down closer to the 0 mark to bring the velocity down, but that increases the height or the probability of finding those. So the higher the temperature, the more spread out the curve is going to be. And again, that's because it is anchored down here at the 0 point. Notice our 400 is more spread out, but the average is still at a higher velocity in comparison, and we have a higher difference in velocity, so we have more probability of, or not more probability, we have more distribution of those velocities and kinetic energy, but it's still the average that's important here. Okay, so let's see how this works on a multiple choice problem. Okay, and I'm going to get you to pause this and actually look at this and see what you guys think. So we have our original sample here. Okay, notice where it is. It says a graph above shows the speed distribution for molecules in a sample of gas at a certain temperature. Which of the following graphs shows the speed distribution, which is really just that curve, of the same set of molecules at a lower temperature? Okay, and the lower temperature is going to be the dashed line, whereas the solid line is this original guy. So what I want you to do, pause for just a second. I'm going to scroll down so you can see everything down here. So A, B, C, and D are your choices. Pause, think through it, talk with your neighbors, see what you come up with. Okay, so hopefully we had the chance to actually think through this and actually pause and think about it. Let's go back down and look at these. We have our original sample. So our average, if we were to draw that line down that center of that curve, that average speed is right about here. If we're going to a lower temperature, what do we want to see happen to the average speed? Well, we want to see it decrease. Why? Because again, kinetic energy is equal to 1/2 mass times velocity squared. If temperature is decreasing and it's the same gas, so mass is staying the same, that means velocity must also decrease. So let's just kind of check out our answers here. We have A, our original speed is right here, and we have B, our new speed is right here. Well, that doesn't make much sense because we go from a lower speed to a higher speed for a lower temperature. So that guy doesn't work. What does it show? Well, it does show a higher temperature. So that would be a great answer if I was looking for what happens when I increase temperature. Okay, check out B. My average is actually the same for both of them if you see what happens. Notice what also happened here is that the number of molecules or the area under the curve decreased. What is that showing? Well, first off, it is not showing a lower temperature because my speed is the same, which would not mean change in kinetic energy. It's showing some of the gas actually escaped. Because the only way I would have a lower probability at the same temperature is if I have less gas molecules. Okay, check out C. I have my original speed right here, and I have my new speed right here. Again, what is that showing? It's showing an increase in temperature. Also, notice what's happening here is the probability is staying the same. So not only is it showing a higher temperature, it's actually showing more gas molecules. So it doesn't work at all. And let's check out D. Okay, we have our original right here, and we have our new right around there. So we do see that decrease in speed. Okay, so we see that lower temperature. Also notice what happens is we end up with a higher hump. Why are we ending with that higher hump there? Well, because again, we're squishing the curve and we're moving it up, keeping our number of molecules the same, because we're keeping the sample the same. So our answer here would be D. Okay. All right, guys, I'm going to stop here again. This concludes the second video, I should say. Hopefully this is working out okay. Feel free to message me on Remind or on the Canvas discussion board if you have any questions. Thanks, guys.